evening. Welcome to Westmont Downtown Lecture Series, Conversations About Things That Matter. My name is Susan Jackson, and I'm a member of the Montecito, that's another role I have, sorry, Westmont Foundation Board. It is the Westmont Foundation Board that sponsors the Westmont Downtown Lecture Series, which began 18 years ago. This series highlights important topics of the day, and our most amazing Westmont faculty brings this information to you. This series is a gift to our community, and the goal for those that attend is to enjoy meaningful and fundamental, lively, and conversations about things that matter. Please do not be shy about asking questions of our fine speaker tonight. Our next downtown lecture will be on Thursday, November 9th at 5:30. The topic will be the challenging geopolitical landscape and the role of foreign aid by Professor Catherine Bryant, a political science professor at Westmont. I'm very pleased to introduce Dr. Kim Deneau, and she will in turn introduce our speaker. Dr. Kim Deneau is the Provost and Dean of Faculty at Westmont. She joined Westmont in August of 2022 and has over 25 years experience in executive leadership in Christian higher education. Previously, Kim worked as Vice President for educational programs for the Council of Christian Colleges and Universities in Washington, D.C. She spent much of her career at Azusa Pacific University as Vice President and Chief Diversity Officer. Kim earned her Doctorate in Philosophy in Psychology at the University of Florida, a Master's of Social Work from Temple University, and a Bachelor of Arts in Sociology at Vanguard University. She was born and raised in Los Angeles and is delighted to be back in California. Kim works closely with the Westmont Foundation in coordinating these special lectures. Thank you, Kim.
Good evening. Well, it is a joy to be here with you tonight. I'm just really taking in the beauty of this rustic beauty as this building. This is my first time in this facility. So it is a wonderful night, beautiful weather, and we're in for an amazing lecture. So let me tell you a little bit about our speaker tonight. Dr. Jennifer Ito is a California resident. She actually completed her bachelor's from UC Berkeley, Bachelor's of Arts in Physics and Astrophysics. She has a Master's of Science in Physics from the University of California, San Diego, as well as her PhD in Physics from University of California, San Diego. Jennifer has produced a number of publications. She's received awards and has taught and done work in Ireland, as well as recently as this summer in Chile, taking a group of Westmont students to Chile to work on telescopes and to do research. She is going to share some amazing information tonight, just in her expertise. Again, astrophysicist, as a physics professor, but a specialty looking at exoplanets and just looking at asteroids in general. I really wanted my own children to come because I thought, hey, come and partake from one of our best. I could tell you many more things, including her leadership of women in physics, as well as other awards that she's received, but something just personal about Jen. Jen is just not only a person who has this curiosity, awe, and wonder for science, but she's also a gentle soul, and I found her just to be an amazing person. She loves baking, and I'm waiting to get some of her, the fruition of her goods of her baking, but she's been a wonderful addition to the Westmont family and community. So tonight, please join me in welcoming Dr. Jen Ito.
Thank you very much, Kim. And thank you all for being here. It is an honor and a privilege to be here with you all this evening and to be able to share with you talk about just what's going on in astronomy right now. There's a lot of exciting things happening this week, actually. Well, stuff that happened this past week, stuff that's happening tomorrow and Saturday. Speaking of Saturday, so in case you all don't know, we're gonna be able to view part of an annular solar eclipse in the morning. And so I know that at Westmont, we're going to be having glasses that you can use to look at the sun so you don't damage your eyes. But also I'd like to invite Tessa from the Santa Barbara Astronomical Unit to come up and share about the event that they're having as well.
Thank you, Jen. So if you live out more towards Goleta, the SBAU will be at the Camino Real Marketplace. That's the big marketplace right before Costco. We'll be in front of the theater. We'll be there. We'll be setting up for astronomers, ungodly hour of 7 a.m. And we'll be there. The eclipse starts at about 8:06 and goes till about 10:45. We will have solar telescopes. We will have telescopes that are fitted with solar filters, so you can come out safely. If you've got kids, the Museum of Natural History will have those little glasses available. So come on out if you're not going to Westmont.
Thank you, Tessa. Okay. Kim already did a wonderful introduction, for me. Just a little bit more. So I am from San Diego, born and raised, and I managed to stay in California for my whole academic career and job. I first spent 4 years at a community college, and this was a really formative time for me. It is what helped me get into physics. It is what helped me get into teaching. And so I'm very grateful for that time there. And then, as was mentioned, I have a Bachelor's of Arts in Physics and Astrophysics from UC Berkeley, and then my Master's and PhD is in Physics from UC San Diego. Currently Assistant Professor of Physics at Westmont. I teach Intro to Astronomy, get to teach physics and music this semester, and also physics for our life science majors. And I really enjoy each of those classes, so I'm very grateful to be able to work with them. Research areas. So my background is in what's called cosmology instrumentation. So cosmology being the study of the universe, instrumentation just meaning telescopes. So that is what I did my PhD work in. That is work that I continue on now. The project specifically that I'm a part of is called the Simons Array. And we are studying the cosmic microwave background radiation. So this is radiation that is thought to be remnants from the Big Bang, so very early universe. And we're looking for a certain signal in that radiation to help inform our models of how the universe started and how the universe evolves. Additionally, I have started learning how to work with Westmont's own Keck telescope. And this has been a really neat instrument to start learning about. Some previous projects that have been done with it is looking at variable stars. This is basically stars that vary in brightness. And then exoplanet transits, and you'll learn more about exoplanets later in this talk. And so yeah, it's been really nice with Westmont's Keck telescope. I can actually see what I'm looking at. With my telescopes that I normally work on, it's actually in light that it's in part of the electromagnetic spectrum. It's part of light that you actually can't see. We can't see with our eyes. So it's fun to be able to point your telescope at something and actually see the object that you're taking a picture of. But for For today, I am going to be sharing more about what's happening in astronomy and why scientists have been working so hard to do these projects that I'm about to share with you. So, overview for tonight. Gonna do just a brief introduction of the solar system, just to kind of set the groundwork so that you know kind of areas that I'm talking about in the solar system, objects that I'm talking about. And then we're gonna dive into asteroids and why they're important, what are they, and some current exciting studies that scientists have been doing, even just revealing results this week about certain asteroids that they've been studying. And then we're gonna look completely outside of our solar system and get to exoplanets. And so I'm going to talk about what is an exoplanet and then briefly touch on some studies that the Hubble Space Telescope has done, and then building on that, what the James Webb Space Telescope is also going to be doing and has started doing already. So without further ado, I apologize if in the back this graphic is a little bit hard to see. But hopefully you can get the gist of things. We have our sun here on the left, and then our what are called the inner planets, so Mercury, Venus, Earth, and then Mars. And then we've got this belt here, this kind of asteroid belt. So this is a region that is between Mars and Jupiter that is basically filled with rocky substances, various sizes, made of various things. And then we've got our outer planets, so Jupiter, Saturn, Uranus, and Neptune. And then if you see out here, there's another asteroid belt. And so this is called the Kuiper belt. So it's another set of asteroids. Beyond that, scientists think there's something called the Oort cloud that has a bunch of comets in it. So this gives a general idea of kind of the structure of our solar system. Now, the reason for studying asteroids and the reason for studying exoplanets, well, one of the main reasons for studying both of those is because scientists are trying to figure out how did our solar system form in the first place. There are different thoughts about this, but the main one is called the nebular hypothesis. So you start off with a cloud of dust and gas, and there's going to be, it's a pretty turbulent gas cloud. Eventually, you're going to have a part of it that starts to clump together and form what we call a protosun. And so that's basically your baby sun. And so you have your protosun. As that protosun continues to gobble up the stuff around it, it's going to get bigger. And you also end up having this gas cloud, it's spinning, and so that's going to flatten it into more of a disk. As these processes continue, then once you have your protosun forming, you also have other protoplanets or baby planets forming outside of it that is gathering material in the dust rings around the sun. And eventually, what you end up with is what we know as the solar system, where you've got planets that have cleared out the area around it, whether it's because they've knocked out smaller pieces or it's absorbed into them. You also have your asteroids. And so the asteroids in particular are thought to be remnants from the solar system formation. And so that's why scientists are really interested in studying them, because it's like debris from the formation of the solar system. Now, in this picture, the main asteroid belt here is all very nicely gathered between Mars and Jupiter. But that's more for just making a pretty picture. It actually is pretty spread out. So it doesn't stop it doesn't stop at Mars's orbit. We've got asteroids that are orbiting close to Earth. It also doesn't just stop at Jupiter's orbit either. So, right, most of them are contained between Mars and Jupiter, but they're not just there. So there's some that leak out, if you will, outside of that belt. And so it's going to be a couple of those actually that are more near Earth asteroids that I'm going to talk about. But before we get there, first off, what is an asteroid? So the definition from NASA is that an asteroid is a small rocky object that orbits the sun. Well, to me, it's an interesting history of how we found these in the first place, because we have this law, and I'm gonna not offend any German speakers in the room by trying to pronounce this name. It's two German names, 1772, and it's this mathematical pattern that was found that happened to describe the distance of known planets from the sun. So you have the first number in this pattern, that was the distance to Mercury, from the sun to Mercury. You have the second number, that was the distance from the sun to Venus, and so on. They noticed that there was something missing between Mars and Jupiter. And so that started the hunt for this planet that they thought would be there. And eventually in 1801, on New Year's Day actually, an Italian astronomer found what we now call Sirius. It was, so this image here is an actual image of Sirius. So NASA had a mission in 2018 that was able to take a picture of the surface. And so after they found Sirius, that year, they did more observations to try and determine, like, is this actually the planet that we've been looking for? And at the end of that year, they decided, yes, it was. But then after that year, they found more objects in that same distance. And so Sirius went from being a planet to now an asteroid. So they categorized these objects as asteroid, meaning just star-like, because they watched them move against the background stars. So it was like a star, but it wasn't the same thing as what they were seeing with planets. So it was something different. Eventually, we found thousands and thousands of asteroids. And so now scientists are working on studying more of the properties of them. There are three main types of asteroids, and it's all based on what they are made of. So one of them is this chondrite, or a C-type, which is your clay and silicate rocks. Silicate is the same mineral type, if you will, that also makes up approximately 90% of Earth's crust. There's also the stony type, or the S-type, which is silicate and nickel iron, so a combination of the silicate and now more metals. And then they've got everything else, which they literally call just the X-type. Now these types, though, now can be broken down into three different subgroups, and this is based on what's known as albedo, or just how reflective are they. So the first one they call the primitive type. These are mainly silicates, but have an albedo of less than 0.1. Metallic M-type is predominantly iron, with some mixture of nickel, they think iridium, gold, other precious metals. And the albedo is between 0.1 and 0.3. And then the last type here, enstatite, has an albedo of greater than 0.3. So to put some perspective on albedo, so our moon's albedo, how reflective our moon is 0.07. So it's actually pretty low. The albedo of Venus is 0.6. All right, but Venus is known as the morning star. It's a pretty bright planet in our sky, and so yeah, hopefully that gives a little bit of context there. As far as locations of these asteroids. So I already mentioned the main asteroid belt. These are asteroids that lie between Mars and Jupiter. There's also a group of asteroids known as Trojans, and these are asteroids that orbit with a larger planet but don't collide with them. So they're on the same orbital path as larger planets around the sun. So Jupiter has Trojans. I think Mars also have these Trojan asteroids. And then the last one, near-Earth asteroids, which is just that they have orbits that are near Earth. And sometimes these cross Earth's orbit. And so one example of an asteroid that actually crossed Earth's orbit, crosses it every 6 years actually, is this asteroid 101955 Bennu. So that number out front, that number is just its place in the long list of asteroids that have been found. And this image that you're seeing here is actually a composite of 12 separate images. This is an asteroid that is near Earth. It's orbiting very similarly to Earth as far as it's 1 astronomical unit away from the sun, or 93 million miles. And this was an asteroid that was selected by NASA to try and land a rover on it to gather a sample from it. And the reason why it was picked for that was because it was large enough and it was rotating slowly enough. So one rotation was about 4 hours, whereas you have some other asteroids that will rotate on an order of minutes. And so this one had a slow enough rotation that they could at least briefly touch down, gather some material, and bring it back to Earth. Yeah.
How big is it?
Right, sorry. 1/3 of a mile at its equator. Yeah. Yep. Thank you. Scientists are also hoping that this is going to provide some insight, right, about how potentially life came to Earth. One model is that asteroids with, right, your carbon, water, those kind of molecules landed on Earth, and that's how we have life on Earth. So this is why scientists are particularly interested in being able to gather material from this asteroid. So if you could see this, I don't know, it's gotten darker now, so maybe those of you in the back can actually see it now, but there's a white line here. That is the orbit of Bennu, and then there's a blue line here that is your orbit of Earth. And so at this point here, you see that they cross. Bennu's orbit is slightly at an angle compared to Earth's orbit. And so there was some calculation done to try and get the spacecraft from Earth to the asteroid. But the spacecraft that they sent is fondly named as OSIRIS-REx. It stands for Origins, Spectral Interpretation, Resource Identification, and Security Regolith Explorer. And I will say this is an excellent example of how astronomers name things. You will see so many acronyms throughout this talk. It's amazing. So one of the main missions of this spacecraft is to gather a sample from Bennu, but it also had multiple other cameras on it. It had visible wavelength cameras, it had thermal imaging cameras, it had a laser altimeter, so that's to measure, make a topographical map of Bennu. So there are various other instruments that it also had, and it spent a good deal amount of time studying this asteroid. With its solar panels completely deployed, it was 20 feet in length, and roughly, I think it's like eight or so feet wide. So it was launched on September 8 in 2016. It arrived at Bennu a little over 2 years later, and it was a 1.2 billion mile journey for it. In the 2 years that it was orbiting Bennu before it gathered its sample, it was doing multiple scans of the asteroid using the various instruments that was on it. It also did a couple rehearsals of practicing getting close to the asteroid's surface and then leaving and going back into orbit. So they did some rehearsals before they actually touched down on the asteroid to gather a sample. But they eventually did their sample collection on October 20th, 2020, and NASA has this really neat video. They were able to capture the probe, if you will, that went down and touched the asteroid. So that was pretty cool. Okay. So there were 82 images there, 1.2 seconds between frames, and calculated that it touched Bennu's surface for 6 seconds. And to me, it was a really fascinating, because I work in instrumentation, like the rovers, telescopes, spacecraft, how they make that's really cool to me. So what the mechanism that they use to actually gather the sample is called the Touch and Go Sample Acquisition Mechanism, or TAGSAM. I told you there were acronyms. So, TAGSAM. And what they did was they created this kind of foot. This foot that when it touched the surface, it would actually inject nitrogen gas that would kick up the regolith, which is just the loose material on the top of the asteroid. And then it went into the foot and was trapped in the canisters on the side. So this is the way that they managed to gather some samples from the asteroid. When they left, they realized that they left a pretty large hole, actually. Not a hole, but a pretty good crater. And there were some large boulders that had been moved, and so actually the surface was a lot more loose. The dirt was looser than what they thought it would be. And so there was one statement where they said, it's a good thing they only stood on the asteroid for 6 seconds, because otherwise the foot would have sank into it. So I thought that was pretty cool. All right, so this sample was taken back, stored into a capsule, and OSIRIS-REx came back towards Earth. And so it left the asteroid on May 10th, 2021, and only this past month it got close to Earth. It jettisoned the capsule with the sample in it, and the capsule landed where it was supposed to, in Utah. Which, if you think about that, that's pretty amazing, right? Because the Earth is moving and spinning, the spacecraft is moving, and you've got to be able to calculate that trajectory just right to land where you want it to. So yeah, another really impressive thing. Just yesterday, they did a press release talking about kind of the first results of the sample that they've been finding. So this is an image of inside of the, inside of the capsule, and you can see, so this, if you see a white box here, the image on the right is the zoomed in version of the white box on the left, and you can see all the different dust grains, rocks that they were able to collect. They were able to bring back 8.8 ounces of material, or 250 grams. And this is the largest sample that anyone has gotten from an asteroid. I forgot to mention, this is also the US's first asteroid retrieval mission. It's only been done one other time by a spacecraft from Japan, and they only brought back like 1 to 5 grams, I think, of material. So with this, OSIRIS-REx brought back 250 grams. And so far, what they've been finding is that there is a relatively large amount of carbon, they said 5% by weight, and hydrated clay-like material. And so that is right, leads to this idea of water on the asteroid, or part of the asteroid. And so with this new information, right, working with this new sample, they're going to keep studying it. I think it's going to go out to multiple different institutions for other scientists to also study it. And then it'll inform the model of the formation of the solar system that we have now. So yeah, it's pretty cool. Other results, and by other results, I mean just one, that I'm going to share with you right now. So this is the topographical map that I mentioned of Bennu. It was measured by using a laser altimeter. And so basically what OSIRIS-REx did, what this instrument did, was it orbited close to the asteroid's surface. For about a month, it was 1 mile above the surface, which was the closest that any spacecraft had orbited a small object. It shot a laser down to the surface and measured the reflected signal. And based on how much time it took for that signal to return and knowing the speed of the laser, calculated the distance from the asteroid to the spacecraft. That was for the beginning of 2019. In the latter part of 2019, they decided to get closer. So now they're half a mile. So that is now the new record. They set it already with a mile. Now they set it again with half a mile around this asteroid. And this time they used a slightly different laser instrument that they had on board. It is something that would send 10,000 light pulses per second. And so they were just firing these at the asteroid. The dark blue areas, as I've noted here, the dark blue areas are approximately 200 feet lower than the peaks that are indicated in red. And this is a composite of roughly 20 million measurements. So another really neat result from this spacecraft. So now I mentioned that the capsule with the sample was sent back to Earth, but OSIRIS is not done yet. So now we have the Origin Spectral Interpretation, Resource Identification, and Security Apophis Explorer. So OSIRIS-APEX for short. Next target is 99942 Apophis, which is another near-Earth asteroid, and hopefully it will arrive in 2029. So can mark that in your calendars. 6 years from now, you know what to look for. Yeah. Okay, so those were near-Earth asteroids. There is another mission that, to me, is really intriguing, that is going to an asteroid that is actually in the main asteroid belt, and this one is asteroid 16 Psyche. This was discovered in 1852. All right, 16 is out front because it was the 16th asteroid to be discovered. It was discovered by an Italian astronomer and named after the goddess of the soul in ancient Greek mythology. This one is pretty unique because scientists really don't know what this is. So they think from studies so far, they think it is it's the largest M-type. So M-type was your metallic type. The other two, so Apophis and Bennu, are your C-type asteroids. So those are more common. Those are like 70 to 80% of, or at least our known asteroids so far. So with this, Psyche is a type M, or M-type asteroid, which means it's predominantly metals, iron, nickel, some combination of those. It is orbiting at an average distance of 3 astronomical units from the sun, so it's 3 times the distance from Earth to the sun. And the fun tagline with this one, as scientists are gearing up to study it more, is that this is quite possibly one of the most expensive asteroids, worth something like 10 quintillion US dollars. And if you're not sure what a quintillion is, that's 10 million. So, this one is measured to be 173 miles across and 144 miles long. There is another space-based mission that is scheduled to launch tomorrow. They were hoping to launch yesterday, but weather prevented that. So they're going to be launching this Psyche spacecraft named after the asteroid that it's going to. They're going to launch it tomorrow. And again, another thing to look forward to in 2029, it will arrive at 16 Psyche. So if you happen to be wanting to see something at 7:19 tomorrow morning, you can look out, see if they've launched. I think they said it was still a 50% chance that they would be able to launch because of the weather. I think there's a storm coming through. And so yeah, 50% chance, but it might happen. I think it's 50% chance Friday and Saturday morning. And their window is for roughly another week though. So yeah, can stay tuned and keep your eye on that. So that is all that I have for asteroids and the exciting things that are happening even just this week. With how scientists are learning about and trying to study our solar system. Move into exoplanets now. So, what is an exoplanet? Exoplanet is short for extrasolar planet, so it's just any planet that is outside of our solar system. So far, we have a little over 5,500 confirmed, and there are lots of other objects that we think could be exoplanets, but we need to study them further to determine that. And studying these can be really important because it can give us insight into how just planetary systems evolve in general, right? So when we create a model for our solar system, does that hold up with what we see elsewhere, right? Because we actually see hundreds of thousands of planetary systems. And so yeah, as we're trying to figure out how did ours form, does that line up with what we're seeing elsewhere? So there are different types of exoplanets, and I'm just going to mention kind of the main ones because there are lots of also subcategories within these. So first one is a gas giant. So this one is basically just a large planet composed of hydrogen and or helium, very similar to Jupiter and Saturn that we have. There have been 1,748 of these that have been confirmed. And this example that I have here, Kepler 7b, was discovered in 2009. It is larger than Jupiter, but scientists have measured it to be less dense, so it's actually only half the mass. It is 3,000 light years away. And if you notice, there's this, in this you notice the name is Kepler 7b with a letter after it. You'll find that as I'm going through these different exoplanets, all of these are going to have some sort of little letter after it. And that's the naming convention. So the planets, their main name is after the star that they're orbiting. So this exoplanet is orbiting Kepler 7, named Kepler 7 because it was discovered by the Kepler spacecraft. And the star is object A, typically. So then anything after that, anything orbiting it would be B. So you have your next planet would be B. Planet after that, that's orbiting further, would be C, and so on. And so as you see these letters, you can kind of guess whether or not it's the one closest to the star or farther away from the star. For this planetary system, they found only one so far. So Kepler B is by itself right now. But yeah, wanted to point out that naming convention so you know what that's about. Okay, second kind of exoplanet is Neptune-like, a very original name. You can guess what that is all about just by the name of it, right? So it's a planet similar in size to Neptune with hydrogen and helium, dominated atmospheres, and cores of rock and heavier metals. Confirmed discovery so far is 1,895. This one is an artist rendition of one that was discovered in 2010, 463 light years away, and that is roughly 27 with 14 zeros after it in miles. Sorry, I didn't do the conversion for the one that was 3,000 light years away, but you can guess it's more than 14 zeros. Yeah, anyway, it's far. The mass is roughly 22 Earths, has a radius of half of Jupiter, and so far just this one planet has been found around this star. And again, the star's name is based off the observatory that discovered it. Another type called super-Earths. So this is a larger planet than Earth, but it is largely made of dense gas. There have been 1,674 of these confirmed so far. This one in particular, Cancri, was discovered in 2004, 41 light years away. And this one is fascinating to me because this one is actually part of a binary star system, and there are 5 exoplanets orbiting the main star. So binary star system just means 2 stars that are orbiting each other, and then you've got 5 exoplanets orbiting that. And so this is one of them. And then last but not least, we have our terrestrial planets. These are basically just rocky planets like Earth. There have been around 200 confirmed so far, and this one that I have up here is TRAPPIST-1e, 41 light years away from Earth, discovered in 2017. And this system has actually 7 exoplanets. And so this is actually one of the, if I recall correctly, this is one of the first exoplanet systems that we found. So in case the name sounds familiar, this was in the news quite a bit back in the day when it was first discovered. So we've got all those different kinds of exoplanets. And scientists have been using the Hubble Space Telescope and the James Webb Space Telescope to study more about what these, what these different kind of exoplanets are like. So first going to talk about some contributions from the Hubble Space Telescope. This was launched in April 24, 1990, and is currently orbiting Earth at 17,000 miles an hour. So it takes 95 minutes to complete one orbit around Earth. And one really neat thing I think about this, right? Again, instrumentation person here, that they got astronauts in a space shuttle to go to the Hubble Space Telescope and do maintenance on it 5 times. And it's all worked. Well, more or less, I'm pretty sure it's all worked. So, right, the fact that you can even do that in the first place, to me, is amazing. So, anyway, stuff that Hubble has been studying. So we're back with TRAPPIST, except this time we're looking at different planets, 1b and 1c. Hubble performed the first atmospheric study of Earth-sized exoplanets. Now, they weren't able to determine exactly what the atmosphere was, but they were able to, they weren't able to determine what the atmosphere was. There was still some question of if there even was an atmosphere. If there was an atmosphere, though, they ruled out the fact that it would be what they call a puffy hydrogen atmosphere. So they figured that much out, but they weren't able to, the instrument sensitivity wasn't enough to figure out more. So one of the really cool things is that Hubble laid the foundation like this for a lot of different areas in astrophysics, not just exoplanets. But as scientists continue to get better and better in building instruments, building telescopes, building spacecraft, we're able to improve and build on previous studies. So enter the James Webb Space Telescope. I'm sure many of you are familiar with this, JWST. It was launched on December 25th, 2021. And currently, it is orbiting what's called the second Lagrange point in the Earth-Sun system. So in this graphic, we have the Sun, we have the Earth here on its orbit, and we have this point. And there's this point that the JWST can orbit around that will also has its own orbit. And so these are special types of points called Lagrange points, where the gravitational pull between the sun and the earth is perfectly balanced. So it creates this stationary point, so to speak, that we have sent actually lots of different spacecraft to orbit around. And so, because the pretty pictures from JWST are really cool, I'm going to show just a pretty picture that has nothing to do with this talk. This is one that was released 2 days ago. It is NGC 346. NGC just stands for New General Catalog. It contains over 7,000 objects, whether it's galaxies, star clusters. This one in particular is called an open star cluster. It is basically a loose group of stars, and scientists think that this is a star-forming region. So your bluer colored areas represents more silicates, and then your redder areas are dust that is heated by the stars that are in there. But anyway, back to exoplanets. So JWST revisited TRAPPIST-1 and did a study to see if they could further determine what the atmosphere was, or even if TRAPPIST-1b has an atmosphere. And so what they did is they did this study to measure the temperature of the planet. And the thinking is that the TRAPPIST-1b is such that the same side of it faces its star. And so if it has an atmosphere, the heat that it gets from the star would then be distributed across the planet. If it doesn't have an atmosphere, then it won't be. And so they took thermal measurements, and what you see here is this is temperature of the Earth that was measured, temperature of Mercury that was measured, and then they have two models on the bottom here. So the one on the left here is if TRAPPIST has an atmosphere. The one on the right is if there is no atmosphere. And based on their measurements, what they found so far is that it lines up most closely with not having an atmosphere. So yeah, one of the neat ways that JWST is following up, right, on studies from Hubble. And yeah, learning new things about our planetary systems. Another really neat thing is that JWST also confirmed its first exoplanet earlier this year in January. So this is an object that was thought to be an exoplanet, but scientists weren't really sure. So JWST picked it specifically as something to go and study, and they are now certain that it is an exoplanet. So this one is 41 light years away. Again, that's 24. I think it's 24 with 13 zeros after it. That's how many miles. And in this system, this is the only known exoplanet so far. Now, there are multiple different ways to discover exoplanets. The way that JWST did this one is by what's called measuring, or the transit method. It's called the transit method, where you measure what's called a light curve. So the light curve basically looks at how much light disappears when the planet passes in front of the sun, in front of its star. And so this dip here that you see is the drop in brightness as the planet is passing in front of the star. This transit lasted about 40 minutes. And so this is how JWST determined that this exoplanet was actually there. Another way that JWST has been studying exoplanets is actually looking at the atmosphere and looking at the spectrograph, or the different colors of light that are coming from it. So when you have the planet passing in front of its star, right, the starlight can come through the atmosphere, and certain elements in the atmosphere will absorb different colors of light, and so then what you get is everything else. And so based on that, scientists can determine what elements are inside an exoplanet's atmosphere. So K218b is a really fascinating one because scientists aren't sure what the results mean. So this is a graph of the different wavelengths of light that they're seeing, and you can see it's grouped. So there's methane, there's carbon dioxide, dimethyl sulfide. One thing that scientists note is that there is no ammonia, which in their models is consistent with having some sort of water ocean underneath the atmosphere. But that's the question, because not all scientists agree on that. Some scientists think that, well, just because there's no ammonia, there's some other chemical reaction going on in the atmosphere that we don't know about yet. You guys see the slide? Okay. Well, actually, that was basically my last slide. So, summary. So, right, we are still discovering and exploring exoplanets, right? We're finding new ones, and we're still learning about the ones that we found. And scientists are hoping this will help inform models about how our solar system came to be, how other planetary systems came to be. And then we're also still doing a lot of studies just in our own solar system. Right, so you can keep 2029 on your calendar and see what kind of fun things happen then. So yeah, just wanted to share, there's a lot of stuff that's going on, scientists are doing to try and still understand just our solar system and our universe. And I hope that, you have all enjoyed this talk and learned something tonight. And we'll look up to the sky more often as you walk outside at night. Thank you very much. So I guess, I'm happy to answer any questions.
How about tracking the next asteroid that's coming towards Earth?
Yes, tracking the next asteroid coming towards Earth. So, let's see. Both, so Bennu was definitely one that scientists thought might hit Earth at some point, especially because it crosses Earth's orbit every 6 years. So that was another goal, if you will, of studying that asteroid, in particular that one, because then I think scientists hope that, right, as we know what it's made of, we'll better know how to defend ourselves against it in case it does happen. I think, though, they calculated that it's not likely to happen within the next century. So we have some time. And let's see, I think Apophis also was one that, another near-Earth asteroid, another one that they thought might hit Earth, but as they've studied that one as it's gone around, also not one that we would need to worry about anytime soon. So, yeah.
Could you elaborate a little bit, if you're a telemetric person, on the frequencies, the size of the antennas, and the power that's used to get this information?
Frequency and the power.
Antenna size, and power.
Frequency, antenna size, and power. Let's see. So I don't know the specifications for each of these spacecraft, unfortunately. Right, with JWST, it has a larger primary mirror, so we'll be able to gather a lot more light from that versus Hubble. And they both have, so let's see, we'll pull up JWST because that one's pretty. They both have different kinds of instruments that are on them. Some of them are optical instruments, so they'll see visible wavelength light. Some of them are near infrared, so that's more closer to your thermal imaging. And so a lot of, like, even the, this picture of NGC 346. This one is this one was taken with the near infrared camera. And so then there was some working on it to give us this image. I'm not sure.
Get the information back to us, the microwave that they use. That's what I was interested in.
Oh, you mean getting the information back to us?
Yes.
Ah, I see. Apologies.
Yeah.
No, unfortunately, I don't know anything about that.
That's right.
Yeah, I mean, typically you'll have high gain and parabolic dish and a low gain. So the idea is high gain will give lots of information. But if your satellite got discombobulated, you need the low gain to be able to reset it. And that would be true of almost all satellites.
What size of the dish is it? The Earth obviously is big, but the one that's a long way away.
Well, for instance, she said with the solar panels, it was like 20 feet by 8 feet.
Okay.
But your antenna itself would have to be quite a bit smaller than that.
Yeah, sure.
Yeah, I don't know. Oh, okay.
Yeah, I'm not sure. I don't know if you can actually see the antenna on this one though. But no, thank you, Ken. Yes.
Have you studied much about the asteroid that did collide with the Earth during the end of the dinosaur age, during the landing of Mexico? Created quite a change in the Earth's atmosphere for several centuries.
Right. Yeah. No, the question was if I've studied the asteroid that is thought to have destroyed the dinosaurs and changed the climate of the Earth. No, I have not, unfortunately. That's an excellent question. Yeah.
Yes, you made reference earlier when talking about exoplanets. You mentioned that by a two-star system, and with planets rotating around them, but they also rotate around each other, the stars themselves.
Yeah.
And I'm not hard time imagining how that all works.
Yeah, I agree. Yeah, so there are models that will generate, like, out of the gas clouds, there are models that will generate a binary star pair. And so based on gravitational forces, yeah, it is something that is possible. I don't know more details of, like, specifically, what makes it possible, I guess. But yeah, it is definitely a fascinating thing to see. Yeah.
You mentioned the exoplanet being discovered with the dip in the intensity.
Yes.
The time factor is also connected to its orbital period, which gives you the distance. How do you distinguish between the eclipse being off the diameter and having a shorter eclipse time versus just being further out in orbit and moving, or closer in orbit and going faster with the eclipse? Because you don't really know where the eclipse is taking place. Is that, across the diameter of the star or across the top of it?
I see. Right, let's see. Let's see. If you, I guess the relative, I guess the size of the exoplanet is dependent on just, just how much of the light from the star that it blocks. So whether it's going, I guess, whether it's going across the main part of the star or even just a part of the star, I guess there's the assumption that the whole planet is passing in front of the star, but you just need to know the amount that is blocked to know the size of the star. Oh, sorry, size of the exoplanet.
And then what about the orbiting distance from them?
Oh, the orbiting distance, right? So the right. So even I guess, even if it's orbiting at a diagonal, there's going to be some plane where this planet is orbiting around the diameter of the or the equator of the star. Is based on the formation models, because as the gas cloud collapses, it's going to form a disk around the center, like around the equator of the star, if that makes sense. So whether that's tilted or not, it's still going to be going around a I guess the diameter of the star. So whether it's a large orbit or a small orbit, it's not going to be going around like the top third of the star or something like that, based on the formation. Based on what we've seen with how the gas cloud would collapse, it's going to form a disk around the center of the star. It's not going to form it like around the top of it or the bottom of it. Sorry, does that? Hopefully that gets to your question.
In the formation, it's always going to go through the
Yeah,
center. So
yeah.
Going through the top third, it's not going to possibly.
Yeah.
Okay.
Yeah. Thank you for that question. Yeah.
Jen, thank you so much for your presentation and just your passion for this area. So I think my question is really more, what drew you to this particular field? And obviously your love for it, but I'd love to know more. Why astrophysics?
Thank you. Honestly, it's just I grew up looking at the stars at night. I was very blessed to be raised in a rural area, and so a lot of nights were, if there weren't any clouds in the sky, it was a pretty clear night. Could see the Milky Way, could see constellations, and just really would love sitting outside watching the stars, sitting out there long enough that the stars would shift position. Right, so sitting out there for hours. And then when I was in undergrad, I knew that I wanted to continue on and get my PhD. I tried, what did I try? I looked into sort of nuclear physics. Sorry, Bob. I looked into nuclear physics, but I was like, I think I'm gonna stick with astrophysics. And so that's when I started taking classes that Berkeley offered in astronomy and astrophysics, and really enjoyed it, and continued on with that with my PhD. So, yeah. Thank you. Yes.
I see the really fun acronyms on the screen, and I was wondering if you have any other fun acronyms that you have run into in your research or something?
Do you know of any fun acronyms that you've run into in your research?
Yeah, there's a couple. One that stands out is there's one called Polar Bear. I'm not sure if you're aware of it.
Oh, I think I have heard of that one. Yes, anyway. That gentleman is one of my research students, everyone, so that's why. Yes. So, I'll finish that one and not leave you all hanging with that. So Polar Bear. Polar Bear is the name of the camera on the telescopes that I work on. So the whole project is called Simon's Array. The camera itself on the telescope is called Polar Bear. The story that I've been told is that it's called Polar Bear because we're looking for light polarization of the CMB, so that's where the polar comes from. And bear is the mascot of Berkeley, and that's where the project started. So that's where we get your polar bear from. But it is a pretty fun mascot. So, sorry, yes.
So when I studied astronomy, we were taught there almost certainly are exoplanets where we would never ever be. What's your forecast for the next few decades? What are we going to learn about exoplanets?
That's an excellent question. I think there's no limit to what we can learn about them. We'll probably find more of them. There's still more on the list that need to be confirmed. And then continue studying atmospheres, finding ones with different atmospheres. Maybe we'll continue to find ones with no atmospheres, find ones with atmospheres that are just completely different than what we're used to. Even this idea, the super Earths, one of the categories of exoplanets, we don't have anything, I think we don't have anything like that in our solar system. And there are other ones that are like just smaller than Neptune or just larger than Earth that we see in other planetary systems that also we don't have in our solar system. And so there are even new, our solar system doesn't have all the kinds of exoplanets that we're starting to categorize. So yeah, I think kind of space is the limit, sky's the limit, space is the limit, I don't know.
I just want to make a quick comment. So Dr. Ito is really providing some groundbreaking opportunities for Westmont students to do research. So my understanding is that Michael and another student, Jacob Nelson, were one of the only very few selected students to ever set foot on the site, the Simons Gray site, and maybe the only students to make significant contributions to the hardware of that site. So pretty remarkable, actually.
Yeah, no, it is a dangerous, it is a fairly dangerous environment to be in when we're up at the telescopes in Chile. We're at 17,000 feet, so you need to wear oxygen. You're at half atmosphere. And so, yeah, traditionally we have not had undergraduates come and work with us up there. It's always been graduate students, postdocs, PIs. So it was really neat to be able to take Jacob and Michael and let's see here if I can pull this up. So these are my two students at in front of the telescope that the front of the telescope that I mainly worked on in graduate school. This is the second of three, affectionately known as Polar Bear 2B. And so, we spent 4 weeks in June this year doing some maintenance on this. There was a calibration instrument that needed to be fixed, so we were able to work on that and fix that. We were having some noise issues in our readout cables, and so worked on trying to figure that out. Kind of just did whatever needed to be done around the site to try and get this telescope up and going. It's still in the calibration phase right now, but we're hopeful that we'll be able to start taking science data with it soon. So, yeah.
Is that in the north of Chile?
It is in the north of Chile, in the Atacama Desert, yep. Yeah, we're very close to Bolivia and Argentina, yep. So we're kind of on the northern east side of Chile, yep. It's very, ALMA, if you're familiar with ALMA, the radio set of radio telescopes that is commonly talked about out in Chile. They're our neighbors. You can see them from our site. And there are also other handful of cosmic microwave background experiments that are on our same plateau. So that can also be neat to be able to run into other individuals, collaborators, as you're running around in the desert in Chile.
Could you talk just a second about the significance of that region and why
Yeah.
you're
Oh, of course. So the main reason why we're there is because it is a dry climate. So because we're looking at millimeter wavelength light or microwave light, it's kind of close to infrared, not quite, but very close. That signal, the cosmic microwave background signal, is millimeter wavelength light that gets absorbed by water in the atmosphere. And also water emits in that wavelength, and so it also generates noise for us. So we need to find a place that is as dry as possible so that we don't have that moisture taking away from our science signal. So that is the main reason for that, yeah.
I've been to that building.
Okay.
Yeah, it's considered in many respects the driest places in the world.
Yep. Yeah. Any other questions? I'm also happy to talk afterwards. But no, thank you all so much for coming. Really appreciate you being here.